Hello, my name is Roy Simpson. I'm a professor of mathematics at Casitas River College in Sacramento, California. This is actually a second part of a lecture video for intermediate algebra on graphing parabolas. I decided to include this extra video because I know that some instructors will talk about the vertex form of a parabola, and there are some interesting applications using the vertex form of a parabola. So I thought I'd go ahead and use this as an addendum to my everything you want to know about graphing parabolas video. Let's go ahead and recall the vertex form of a parabola. A parabola is dominated or generated by a quadratic equation. In this case, our quadratic equation has a very special format. It's been factored for us, usually using a process known as completing the square. And they give us something like y equals a times the quantity x minus h being squared plus k. Where in this case, if somebody hands it to you like this, h is the x value for the vertex and k is the y value for the vertex. Notice that the h is opposite of what's on the inside of parentheses. That is, if somebody handed you this, y equals 3 times the quantity x minus 2 squared plus 1, you know that the vertex is going to be the opposite of that negative 2. It's going to be 2 and then 1. Okay, so it's just these two will always be opposite numbers. Just like these two right here are opposite numbers. Your parabola opens up if that a is positive. It opens down if that a is negative. Now, a lot of this is generated from graph theory and using the fact that you can use shifts and translations, which is a future lecture, actually. That's why I don't like talking about the vertex form so early. So what I recommend is if you're watching this video and you're not in my class or you're not following a textbook, I would recommend finding my video on shifts and translations for functions and watching that. As of this date that I'm recording, I do not have it up, but I will have it up within another week. So I think that's better video to watch as far as determining how to do these shifts and knowing that the vertex is at HK and understanding why that's true. But for now, this vertex form is something that a pill you'll just have to swallow. So let's go ahead and use it. And the example I'm going to do is slightly different from what I wrote down as my example in the previous page, this example right here. I wanted to actually have a -4 there instead of a +1, just for a specific reason. And when we go to graph this, actually I should use a thicker pen for this. We're going to go ahead and set up some axes here. And I'll read right off of this that the vertex is at x equals the opposite of that -2, which is going to be +2, and then -4. So our vertex, I'm going to go forward 2, 1, 2, and then down 1, 2, 3, 4 units. So here's our vertex. I'll just write in here 2, -4. And that's the power of the vertex form. The other power of the vertex form is that they tell you, that tells me that it's opening up. But if I'm really going to do this properly, I'll still need to plot points. Good points to pick would be the x-intercepts, finding the x-intercepts. Another idea is if you're not being asked to find the x-intercepts, is to use the wiggle points. In other words, the points that are like x equals 2, but they're plus or minus 1 away from that. So in other words, try x equals 1 and x equals 3. Instead of x equals 2, you just hop backwards 1 to x equals 1 and forwards 1 to x equals 3. Plug those points or those values in for x into your equation here to find out what the corresponding values for y are. And actually I'm going to do that because I want to point something out here. So for our points, I'm going to try x equals 1 and then x equals 3. Again, because it's on either side of x equals 2. When I plug in x equals 1, I get 3 times the quantity 1 minus 2 squared minus 4. 1 minus 2 is a negative 1, but being squared, that just turns into a positive 1. So this turns into 3 times 1 minus 4, or in other words, a negative 1. So let me plot that point. When x is 1, y is negative 1. Something I want you to notice about that as well is that essentially what I'm saying is when I wiggled my x value back by 1, it jumped up by a value of 3. And notice that that 3 is actually right here. It only works when you wiggle by 1. So don't wiggle by 10 and think you go by 30 or something like that. But when you wiggle by 1, your y value changes by that a. It's kind of an interesting little result. So same thing here. Try x equals 3. Just plug in 3 for x here. So when you do this calculation, you'll also find that that turns into 3 times 1 minus 4, or in other words, you're back at negative 1. In other words, if I step forward a step of 1, again, my y value changes by that coefficient, which is the number 3. It rises up by 3. And now I could connect these points. Now before I go any further and connect those points, I do want to talk about finding y-intercepts and x-intercepts, so I might as well just do that. The y-intercept is very easy to find here. You just let x equal 0, so you'll have y is equal to 3 times a negative 2 being squared minus 4. A negative 2 squared is 4 times 3 is 12 minus 4 is 8. So this tells me that my y-intercept occurs at a height of 8. 5, 6, 7, 8. So it's way up here actually. 0, 8. And my x-intercepts, well, before finding them, I could determine how many I have just by using the discriminant, but there's really no reason. I know that my parabola is opening up, so I'm going to hit the x-axis twice here because the vertex is below the x-axis. So I'm not going to bother using the discriminant. I'm just going to let y equal 0 because that's what happens when you're at the x-intercept. The y value is 0. And I'm going to solve this quadratic equation. This is one of those special quadratic equations where everything's written so that we only have one version of our variable here. In other words, I do not see blatantly in front of me an x squared and then an x. I just see a regular old x. So this is actually easier to solve. Add 4 to both sides. I should write my little implication there. Divide both sides by 3. And I'm going to gain a little extra room by writing over here. Take the square root of both sides. When you take the square root, remember you get the plus or minus. Clean up the left-hand side there. I'll split the radical. So I have the square root of 4 in the numerator and the square root of 3 in the denominator. Square root of 4 is just 2, so let me just write that again. 2 over root 3 is equal to x minus 2. And then finally, I'll go ahead and add 2 to both sides. So when I do that, I get 2 plus or minus 2 over the square root of 3 is equal to x. These are my x-intercepts. They're at 2 plus 2 over root 3 and 2 minus 2 over root 3, which is a very interesting concept. Basically, they're saying that they're centered at the value of x equals 2. One happens to be at 2 plus 2 over root 3. Actually, I should have done that in a different color, so let me do that. So I start at 2 and I go plus 2 over root 3. And the other one's that starts at 2 and goes minus 2 over root 3. Something like right there. You can plug these into a calculator to find the actual values, but I'm just going to say they're right about there. And now I can connect everything up. And I have all of my values. This is 2 plus 2 over root 3, comma 0. And this x-intercept is at 2 minus 2 over root 3, again, comma 0. So let's go ahead and connect these up. Not going to be the best graph in the world because I'm freehand drawing this. It looks something like this. something like that. So that's how you graph using the vertex form. Notice that if you're going to graph properly, you should always label y-intercepts, x-intercepts, and the vertex. And actually, if you're dealing with a quadratic, most people like you to also note the axis of symmetry, which is essentially that mirror axis. It occurs at the x value of your vertex. So this is at x equals 2. It's a vertical line, x equals 2. Now, something that I failed to mention in the last lecture, it's not that big of a deal because I think that it's more common sense than anything else, but I should mention that is considered to be the minimum point. It's the minimum point because, well, it's the lowest point on the graph. If your graph opened downwards, so let me open up a new window. If the graph opened down like this, then you would have a maximum point. And right now, since we're not doing applications, this is not so important, but when you start doing applications, you'll be asked quite often to find the maximum value of something or to minimize the cost or something like that. And that means find the lowest or the highest point on a parabola. The next style of example we're going to do that involves using the vertex form, or not really, is finding the equation of a given graph. There are a couple things that you could do here. One, always note that if you're going to be asked to find the equation of a graph, at least at this point, you should use the vertex form, unless they explicitly give you x-intercepts, which in this case they have. So there's actually 3 ways to do this, which is unfortunate. Or maybe it's fortunate if you like options. One way is to just use the vertex form of a parabola and a point. So just like a line, when you want to find the equation of a line, you need a slope and a point. In this case, you'll need a point being the vertex and another point that's not the vertex. If you look at this, the vertex at least appears to me to be at x equals 1, y equals, let's see, that's negative 10. So that must be negative 12, negative 14, negative 16. These must go by 2's. Okay. So I see that my vertex is at 1 comma negative 16, and then I could kind of eyeball another point on this graph. Now there's several places where there's another point. For example, this one looks like it crosses the grids right there. That's at x equals 3, y equals a negative 12. Or I could choose this one right here. That's at x equals 5, y equals 0. That actually looks like a better point, to be honest with you. So let's go ahead and at least plug in the vertex here. So this implies that y is equal to a times x minus the x value for the vertex, so x minus 1, quantity squared, plus the y value for the vertex, which is negative 16. Well, okay, I don't have to write that as a negative plus a negative 16. I could write it as a minus 16. And now the only thing that I'm really missing from this equation is the value of a. And I could find that by plugging in any point that exists on this parabola, just like you're working with lines. You just plug in any point you want. And I'll tell you, the easiest point to me is to plug in is this 5 comma 0. So I'm going to let x equal 5 and y equal 0. Because that point exists on my parabola, so it should definitely satisfy this equation. So if y is 0 and x is 5, I get the following equation. 0 is equal to a times the quantity 5 minus 1 being squared minus 16. That's 4 squared. So we get 16a minus 16 is equal to 0. Add 16 to both sides and divide by 16. You'll get that a is equal to 1. And here we have our equation. Just plug that in for a here. And our absolute equation is y equals 1 times x minus 1 quantity squared minus 16. It's very, very similar to finding equations of lines. You need two pieces of information in both cases. And in reality, often when you're finding the equation of a graphed parabola, if they don't give you the vertex, you only need three pieces of information. The vertex is so important it almost counts like two pieces of information. Same thing actually with x-intercepts. X-intercepts are almost exactly the same idea. So I suppose maybe I should write this down in some concise format. So to find the equation of a parabola, there's three things, or three options. If somebody hands you a vertex, that's worth a lot. A vertex essentially is worth 2 points. So if they hand you a vertex and another point, you can find the equation of a parabola. In general, you need three pieces of information. But like I said, if somebody gives you a vertex, that's worth 2. It's like, it's just like, each piece of information is like a free throw, and that's just like a normal shot. So anyway, a vertex is worth 2 points, and then if they hand you a point other than the vertex, then essentially they've given you 3 pieces of information. And if they do that, you can use vertex form, and that's what we just did. So that was the method we just used. They gave us a vertex, and they actually gave us more than one other point. They gave us a bunch of other points, in fact. But I just used a vertex, plugged it into the vertex form, and then used the extra point that I could find on the graph to find the value of A. However, sometimes they don't straight give you the vertex. So if, on the other hand, they give you a couple x-intercepts and a point, so that's 3 pieces of information, you can use that to rebuild the equation. And I'll give you an example of that in a moment. And finally, if they just give you 3 random points, it's not a vertex, just 3 random points on your curve, then you can still find the equation of the parabola. And again, it will be in standard form. But that will be for a future lecture. We're going to do that in the next lecture, actually. For now, I want to, since I've already shown you way number 1, I'm going to show you how to do the second method using the very same example that we just played with here. So what I'll do is I'll go ahead and erase all of my work. Just remember that the equation that we got was y equals the quantity x minus 1 squared minus 16. This is the equation for this parabola. So I'll go ahead and erase everything else here and restart, and just pretend that they didn't give me that vertex. I know that I'm staring at it, so I know that they probably gave me a vertex, but let's pretend that they didn't give me the graph. Instead, they said you have a graph that goes through 5, 0, which is an x-intercept. Let's see, that's negative 3, 0, which is an x-intercept. And then they give me one more point, and let's say that's the 3, negative 12. Okay. Given those 3 pieces of information, I could still rebuild the equation. The way I could do this is say, well, listen, if they gave me x-intercepts, that means that when I plug in 5 to my equation, the y value is 0, and when I plug negative 3 into my equation, the y value is 0. In other words, x minus 5 must be a factor, and x minus a negative 3, or in other words, x plus 3 is a factor. So my equation looks something like y equals some number times x minus 5 times x plus 3. Now let me convince you that this is true. I told you that they gave us x-intercepts of 5 and negative 3. Negative 3, and that's the positive 5 right there. So that means when I plug in negative 3 into this equation, it should turn into 0. And it does, right? If I plug in negative 3 right there, I get negative 3 plus 3. So that is 0. 0 times anything else is still 0. On the other hand, they also told me that 5 is also a solution or an x-intercept. So if I plugged in 5, I would get 5 minus 5 is 0. 0 times anything is 0. So again, that works out. I just don't know if I'm multiplying, like if my equation, my quadratic equation in the end has like 3 times that or 1 times that or 1.2 times that. So that a is unknown. But I almost have the entire equation written out right now. In fact, what I can do is I can multiply this stuff out. So you can see my equation kind of looks like a times the quantity x squared minus 2x minus 15. Now how do I find that a? Well, they gave me one other point for a reason, so that I could plug it in. So let's let x equal 3 and y equal a negative 12 to see what that a is. So letting y equal to a negative 12 and x equal 3, we get the following. Let's see, 9 minus 6 is a negative 3, minus another 15 is a negative 12, so that implies that negative 12 is equal to a times a negative 12, or in other words, when I divide by both sides by a negative 12, a will equal to 1. Aha! So my equation must be y equals 1 times that trinomial, or in other words, just x squared minus 2x minus 15. Now, if you take a look at this equation that we arrived at, it sure doesn't look like this other equation that we got when we did it using the vertex method. But if you multiply this out, you'll get x squared minus 2x plus 1 minus 16, which is actually x squared minus 2x minus 15. So these two are actually equal. They're very, very similar, or exactly the same, sorry, they're equivalent. So those are two methods so far that you can use to find the equation of a parabola if they give you points on the parabola or if they give you a vertex and a point, something like that. Now, like I said, there's another method, and it's actually probably the most preferred method because it's one method to rule them all, I guess, one that will always work. But I'll talk about that in a future lecture, the next lecture, in fact. So let's go ahead and approach a word problem, not very much of a word problem, but just a problem that doesn't have a graph initially. So write an equation for a parabola with vertex at this point and x-intercept at that point. Now, again, this is what we just mentioned a moment ago in this list. If they give us a vertex and a point, we're pretty rocking. We don't need anything else. So let's go ahead and write down the vertex form since they've given us vertex. Now they've told me the vertex is at 0, negative 3. At x equals 0, so in other words that h right there is 0. And this k right here will be a negative 3. So let me substitute those in. I get y is equal to a times x squared minus 3. And then they tell me the x-intercept is 2, 0. Now I don't really care that's the x-intercept. All I really care about is that it is a point that I can plug in to find this value of a. So let me let y be 0. Again, I'm substituting in because they've given me values. And I'll let x be 2. So I get the 0 is equal to a times 2 squared, which is 4, minus 3. Add 3 to both sides, divide both sides by 4, and you get the following. A is equal to a positive 3/4. So my equation, which is almost right there, is going to be y is equal to 3/4 times x squared minus 3. And you can plug these points in, by the way, to see if they work. Like, for example, when x is 0, y is actually a negative 3, so that works out. And when y is 0, you could easily find out that x will actually be 2. Now, as a final kind of tricky example, it's not really tricky, but a final interesting example is that we're being asked to find an equation for a parabola with vertex at 0, negative 3 and having no x-intercepts at all. Now, I'm just going to quickly graph this. 0, negative 3 is right here. And if we don't have any x-intercepts, that means that we're opening down, right? There's a lot of parabolas that actually satisfy this. So let me just write the vertex form first. Ax minus h being squared plus k. We are going to substitute in for h the value of 0, because that's what the value of x is for our vertex. And for k, we'll substitute in negative 3. So I get that y is equal to a times x minus 0 being squared minus 3, or in other words, y is equal to ax squared minus 3. And at this point, I need to find out what a is, but I have no other point. They didn't give me a single other point on this parabola. So I ask myself, is it that important that they didn't give me a point? Or can I choose any point that I want? I can't choose any point I want. I can't choose like 1 for a, because if I did, it means it would open upward and it would eventually hit the x-axis. But I could choose a value like negative 1 or negative 10 or negative pi for all I care. I'll choose negative 2.8x squared minus 3. But anything with a negative coefficient on x squared would be correct. Because any graph, anytime you graph this parabola, it will always open down. It will always have a vertex at 0, negative 3. So therefore, it will not have any x-intercepts. That's it.